Yeah, we'll get started in just a few minutes. Let's see. Yeah, through about 4 minutes. Okay. We'll get started in just a few seconds here. I think I'm going to try. Okay. Okay, let's get started. Can you all hear me okay?
Yeah, we can hear you fine.
All righty. So So I'm just going to jump right into it, and then I'll try and leave a little time at the end for questions. And if you have a burning question you need to ask right now, go ahead.
Oh, Professor, I had a question about quiz 1.
Yeah.
Is that the syllabus quiz, or is that for like the actual lecture 1? Because we only get one attempt and I didn't want to press it.
Yeah, it's
on
lecture.
accident.
It's lecture 1.
Oh, okay. Thank you.
Yeah. Yeah. And yes, that's what that is.
And also for the homework, I was seeing that you put like a pre-list based off your textbook.
Yeah. So it's going to be a little confusing because I'm doing, I haven't taken all the information out of the face-to-face Blackboard course that doesn't apply, but there's quite a bit that doesn't apply. And so for this course, your homework's going to be basically at the end of the chapters. So let me show you. So here's the book. This is what the book looks like. And it's an online book. And what happens is as you go through, there's some knowledge checks, and these are fine. These don't count against you one way or the other. They're just for you to kind of check. But as you go down, another knowledge check where there are questions. But then at the end, then there's a little quiz. And when you click that, there's flashcards which go through all the definitions, which you're welcome to do. So algorithm, and then you can flip it over. This is a plan, rule, or procedure for how to accomplish some task. Typically, this would be executed by a digital machine. And you can go through accuracy and analog, digital, parallel algorithm, quantized, precision, serial algorithm. And it goes through all these are some of the main terms I want you to get. And these are just to kind of review. And then you can do the quiz down here. And so it'll have questions like analog offers greater precision. And this one's pretty easy for data. And you answer yes or no. The next one's an algorithm where we must complete each step before we can start. The next would be considered a parallel algorithm, true or false. And then a glass thermometer may vary continuously, blah, blah, blah. So this will really constitute your homework per se. Now, I may throw in some additional homework assignments, and you're always welcome to look at the ones that were there based on the Roth book and all that. If you want to mess with those, you can do that. It certainly will help you. It's not going to hurt you. That's for sure. But anyway, and I think I think you get like 2 hours to do the quiz. All right. And then, yeah, submit. Okay, I'm going to cancel.
And so with the quiz, you only get one attempt as well?
No, I think you get 2 attempts. I think that's how I set it up. So yeah, so you can go back and work on it if you mess up. So yeah, I think I did set it up for 2 attempts. All right.
And how many attempts do we have on the homework? I'm sorry.
I think you can do 2 attempts. You can do 2 attempts on the end of chapter quizzes.
Okay.
Yeah. And
thank you for clarifying that.
Yeah. So that's the deal. And let's see. I guess to get back, I have to do this. All right. So let me do the slides here. Let's see. Did I make them big? Not yet. Okay. Yeah. Okay. There we go. All right. So, okay. So, so again, after 3 weeks, we'll hopefully be face to face. So this is the first week. Got one more day this week, Friday. I will do. I am going to. I'll hopefully do new videos for this course. That's what I'm planning on doing. But I will leave up the old videos that were synced to the Roth book. I have posted the Zoom video from Monday, and I'll post the video from today. I'll try and put those. I'll probably put those in a separate folder. I think that's what I did. So maybe I'll look at let me look at the syllabus real quick. Let's see. Where is the content? is this logic design? Yeah. Let's see. That's the online course. Nope, that's this course. So I haven't changed this yet. Okay, I need to do that. All right, well, anyway, we'll get that finished, fixed up. Yeah, so I think I did, see if this is it, or all the videos. Yeah, I guess I put it at the first. So I didn't create a separate folder, but I think maybe I'll do that. So this was the class from Monday. So you can go in this videos F21 and I'll have Zoom class. If you just want to look at the video that I did for the Roth book, you can look at it here. This is from, I think this is from fall 20. Okay. And all these are already on here. So you're welcome to go through them if you want. The books are similar, but they're not entirely synchronized. So if the video is a little out of sync with what we're covering, that's okay, but it'll follow along pretty well. There'll be some things I cover in these that I'm not going to cover in the book because I don't think they're that important. And there'll be some things I cover in the book that these didn't have. So they're not going to be in exactly congruent, but they'll be similar. Most of the material is the same, but yeah. All right, and let's see there. Okay. All right, let me do the slides again. Let's see, I guess I can do that. Okay. So so there are some big changes in emphasis. I'm gonna try and talk about Verilog a little more and C a little more. In the Roth book, they covered VHDL, and I'm gonna minimize that, mostly because we use Verilog within the department, and in the real world, pretty much in the United States, all the chips are made with Verilog and not VHDL. So in Europe, they use VHDL more, but for your purposes, it's probably better to focus on Verilog. So I have a chapter on algorithm development that I think is very important. I also have one about how to think about systems as a composite problem. There's a lot more sort of big picture stuff in the text. Was there a question?
Yeah. Do we have access to this slideshow to follow along, or?
Yeah, I will do that. Let's see. I will put that on Blackboard right now. Let me do that real quick. So back to here.
Thank you.
So let's go back here, content, and so it is in. Take a minute to do this, but it's probably a good idea. So there are slides, but they're the old ones. So I think I'll probably just make a new folder. That would probably be better. Okay. And then we'll submit that. It should be visible, and then we have to move it up here. Forever to do this. And then we go. And we'll call it. Okay. Okay. All right, and that should be the same slides we're looking at. Okay, that's good. It is. All right. Okay, so now you can see them if you want to bring them up. They should be on the web. Okay. So okay. So the course is 3 parts. This is important to keep in mind. So we have the kind of the first third is sort of switching algebra, kind of introduction stuff, the concepts of digital versus analog and binary numbers, number systems, and obviously the theorems of switching algebra. So the second part is where we look at how to take a truth table and turn it into hardware where you have some number of inputs, you have a network of gates, and you have some number of outputs. The outputs reflect the current inputs minus a small propagation delay and transport delay, usually measured in nanoseconds or microseconds. The last part of the course is sequential design, and that's where we take a number of combinational networks and include a set of flip-flops and a clock, and we go through a number of different states based on some history of previous inputs. So the sequential design always has some memory of previous inputs, some history, whereas a combinational design has no history. It's just whatever you see is whatever the inputs are, that's what you get. And when they change, the output changes rather quickly, minus a small delay. But in the sequential design, we usually have a clock, and we usually step through a number of states based on the various inputs. And whatever state we happen to be in fact, does depend on some previous history. Maybe an extensive amount of previous history, maybe a very small amount. Just depends on whatever it is the system is. So those are the 3 parts. This first part, where we're dealing with switching algebra, number systems, codes, various things, the combinational design part, and then the sequential design part. All right, we're going to use concepts for digital systems. We're going to hopefully give you some insight how we manage complexity, how we manage, and one of the ways we do that is with layers of abstraction, but there's some other techniques we use too, regularity, conformity, things like that, hierarchical. And then there will be a group project we'll do right before we take the second midterm, and hopefully that'll cover the first part of this and most of the second part. Well, the second part, combinational design, and hopefully that'll make most of that make sense. And then the sequential design will cover and then have a final. Okay, so layers of abstraction. This is a concept that's it's not too difficult to grasp, but it can be confusing. So one way to think about this is if you think about your grandfather or your grandmother using email, or maybe on Facebook, and what they're doing, they obviously they're using very complex computer systems and programs and low-level drivers and displays and input devices to do this, but they don't know anything about that stuff. All they know are a limited subset of the instructions that the application allows them to use. There's probably a whole bunch of features in the application they've never heard of or don't know how to use. And the way they can do that is they're working at a fairly high level of abstraction where all this complexity that's actually making it work is hidden to them. They can't really see it. They don't see it. And it's hidden away so they aren't distracted by it. So here's grandma using Outlook to email her friends. And this is what grandma sees. Even this is pretty complicated. But what she doesn't see is beneath this Outlook application, there's a Windows operating system running with a lot of other applications running at the same time, a lot of supporting DLLs running to drive keyboard, mouse, disk input output, GUI interfaces, graphical features, graphical processing. And then if she prints something out, her printer drivers, her various fonts that she's seen, her various printer fonts, her various display fonts, on and on and on. These DLLs are using low-level drivers. The low-level drivers are talking to actual chips and logic gates, and the logic gates are made up with transistors. The transistors are using quantum physics to get their stuff done. Grandma doesn't see any of this because she's working at this high level of abstraction called the application. And that's also how we can design very complicated devices. We build up very complicated devices a module at a time. We debug the module, get the module working, and then we move on. You can kind of think of it like, say, an Army division commander, which might be a full colonel, might be a 1-star, depending. And this 1-star, say, if there's some private down in the 3rd platoon of the B company of the 233rd Battalion of the 2nd Brigade, he doesn't talk directly to that private. He has a whole layer of leadership that he goes through. He doesn't get anywhere close. He probably talks to the brigade commander and maybe sometimes to the battalion commanders, but pretty much he talks to his brigade commanders and they talk to the battalion commanders, and the battalion commanders talk to the companies, and the companies talk to their platoons, and the squad leader talks to the private. If the general officer had to talk to every single private individually, except maybe on the rare occasion where he addresses the entire division in some humongous meeting on the parade field, but other than that, where it's more of an inspirational talk or whatever, but other than that, that commander is giving those day-to-day orders through this chain of command, and it's very hierarchical. He's sort of, well, he's not even at the top. He's got his army commanders he has to respond to, his theater commanders, and obviously the chiefs of staff and the president. So there's a whole chain of command, and it's that hierarchy that allows him the ability to control all these people fairly efficiently. And that's also true in our digital world. We have hierarchy, and that's how we can get things done in a fairly efficient manner. Okay, and part of that though means he has to restrict his behavior to a small subset of brigade commanders. He really can't afford to be screwing around trying to talk to individual privates on any regular basis, because if he does, he won't be able to lead his division. All right, so hierarchy is one way we deal with complexity. Modularity is another way we deal with complexity, and regularity is another way. So those are the key methods we deal with complexity. We have a top-down structure. We break things up into independent modules that we can debug, we can create, and then we can reuse as many times as we want without having to worry about the details, because we've taken care of the module, we know it works correctly, and we've now hidden all the details away. So we just put in stuff, we get out stuff, we don't worry about how it gets done. We know that it's going to come out correctly. And then regularity. We typically require all our transistors to be identical, except for ones that have special functions, like maybe line drivers. But all our logic transistors that make up our logic gates, all our AND gates, they may have different numbers of inputs, but they otherwise behave the same. Our OR gates, same. We enforce this regularity. Everything's going to operate at certain voltages with, we're going to cordon off things that operate at other voltages, so we don't have all that confusion. And so hierarchy, modularity, and regularity are some of the keys to how we deal with these very, very complex digital devices. All right. So digital design. So this whole concept of digital is something I want you to really feel like you have a grasp on. So what makes something digital? Because we live sort of in an analog world, but almost now all of our electronic systems are digital. In our digital world, we have constrained ourselves to allowing our variables, our single individual bits at least, to only have two values, true and false, 0 and 1, whatever you want to call it. Whereas our analog signals vary continuously over a range, and they can take on an infinite number of values. However, we restrict them to a range, so there's a useful range we force them to exist in. But within that range, they're continuous, right? But the problem is we can't read them to an infinitesimal degree of accuracy. We can only read them to a certain level of accuracy, which means for all practical purposes, our analog signals can only be appreciated in a very limited number of values. So because of these things, we have in our digital world, we can because we are limited to these two values, 1 and 0, we have much simpler logical equations. We have much more powerful logical theorems, and we can make our interfaces a lot simpler. All right, so we talk a little bit about in the digital world, our quantities can only assume certain discrete values. So for instance, we have a digital thermometer. I think I've got one here. I'm going to pop on down to it. See where. Here. If you look at this thermometer, it reads to 1/10 of a degree. So you can have a temperature of 37.0, 37.1, 36.9, but you cannot have a temperature of 37.05 or 37.17 or 37.23. It's automatically restricted to 37.0, 37.1, 37.2, or 36.9, 36.8, and so forth. You can't have anything other than a single decimal digit. Here you have an analog thermometer. This column of alcohol or mercury, whatever they make it, in this case alcohol, is going to vary, and as it heats up, it gets longer. As it cools down, it gets smaller, and it runs up this capillary tube, and it indicates the temperature. And this is showing something close to 10 degrees. That'd be 20, 30, 40, and so forth, 0, 10, minus 10, minus 20, minus 30, minus 40. But here's what's interesting, right? How accurately can you actually read this? It does vary continuously. So in theory, it takes on an infinite number of values as it moves along. But for all practical purposes, you can't read an infinite number of values because you can't read it to an accuracy. Probably something like maybe 1/3 of a degree is about as good as you can do, and maybe not even that. That's maybe pushing it. Maybe 1/2 a degree is all you can do. So whereas you can read to 1/10 of a degree very reliably on this digital thermometer, you cannot read that accurately on this analog thermometer. Now you can make it bigger. You can make the capillary tube smaller and the scale a lot bigger. And we do that for basal body temperature thermometers. Actually, we have them vary only between about 35 and 39 degrees. And so we can read them a little more accurately than we could say this. But even though, so if you think about this concept of analog, you would think, okay, because it varies continuously, you have infinite accuracy. But of course, that's completely not true, because you can't read it to an infinitely accurate reading. So what are the advantages of digital? Well, historically, everything was analog, and digital was super expensive and super complicated and clunky and big and bulky. But all that has changed dramatically. And now digital is cheap, it's small, it's fast, it's low power, and it has all sorts of benefits. It's very reliable. You can have your mathematical operations can have almost any level of precision you want to provide for, as long as you don't mind a little more expensive hardware. Although as cheap as it is, you don't have to add much expense to get much greater precision. There's no real theoretical limit. However, with analog, you're always limited by noise. It's a huge problem, and it limits your precision in any kind of analog mathematical operations to just maybe 3 places. It's really a problem. In digital, you have tremendous flexibility typically because you can just change the software, assuming it's our firmware or whatever it's got, and configure it in a way that gives you all sorts of new features you didn't have before. It's very flexible to adjust to changes you want to make. And once you get a digital device working, it's probably going to work very reliably for a good long time. I mean, they certainly can break. They do break, but when they break, they typically hard break. So it doesn't work at all. So you know you're done. You don't start getting, squishy readings and you don't know why. The other thing in the digital world, our outputs are pretty much very deterministically related to the outputs, or the outputs are very deterministically related to the inputs. I kind of said that backwards. And the other main feature in digital is that we can control noise very tightly. All right. In analog, it used to be cheaper and used to be faster, but that's no longer true. Things have changed. Analog systems could not be modified by changing software because they didn't have software. So they were very inflexible. Even small changes in their function could result in just having to develop an entirely brand new device. You might see some analog systems still used with very high power, very high voltage, that kind of thing. And of course, we do have a lot of transducers. Our motors are certainly pretty much, you would have to think of them as analog. A lot of our sensors are analog. Microphones are analog pretty much. Actually, our video cameras are not so much analog anymore. They're pretty much digital, pixel by pixel. But temperature sensors are analog. We just convert them to digital right off the bat. Barometric pressure, light levels, all those things are pretty analog. All those sensors are analog in nature, but they get modified into digital pretty quickly. Okay, so the big disadvantage of analog is that noise comes in and runs everything in the analog world. In the digital world, we have noise also, but we can do a lot of things to manage noise. And once we convert our input signals into a digital format, from then on, we can absolutely preserve the signal in a way that it'll never be degraded by noise, if we want to do that. All right, so any of those historical advantages that analog used to have are completely gone. There's very few places where we use analog anymore. Yeah, and we used to have analog computers. I'm sure none of you've ever seen those, but they were just completely, they were super limited in their precision because the noise that would be injected at every single level would limit, in any kind of calculation with multiple steps, you'd be left with 1 or 2 digits of significance after just a few steps because of all the noise. Whereas in digital, we don't have that problem. There's no limit on preserving precision of our signals. Once we get the signal in, there may be some inaccuracies in the initial signal, but it's not going to get modified or made worse as we process it. All right, so we have made, the logic divine part is sort of how we kind of put together the processing of our signals within a system. So we don't really think of logic design as the system. The system's is a level of, it's an abstraction level above what we're doing. We're down in the weeds thinking about how we're going to make ones and zeros interact with each other. And we're sort of above the circuit level because there's a lot of different ways we can implement any logic expression. We can usually implement it a good number of different ways. So we're sort of between the system level and the circuit level, the device level, if you will. But we're kind of in this logical middle level where we're learning the nuts and bolts of how we, the basics of how we build things to process signals, to do useful things with the signals. All right, here's our classic switching network. For the first part of the course, this is going to be purely combinational, no memory at all. The inputs, some number of inputs, in this case 3, generate some number of outputs, in this case 2. And whenever the inputs change, there's a small propagation delay, and the outputs then assume they're correct signals. And this is just, this is very deterministic. If given a set of inputs, you should be able to predict exactly what the outputs would be. No ifs, ands, buts about it. It's very deterministic. And if for some reason you put in the inputs that should give you a certain output and you don't get it, your system's broken. You've had a catastrophic failure in your system. This is our tip, and this is what we're going to use for the first 2/3 of the course. We're going to talk about inputs, a switching network, and outputs. The last third, we're going to take several networks and put them together to create, along with some memory elements in the form of flip-flops, to create a sequential design, or a state machine, if you will. And we're going to learn all about that. But for the first 2/3 of the course, we're just going to, this is kind of what we're going to deal with. And usually maybe just only one input for most of our things. Sometimes no inputs, actually. When we get the sequential design, we may have a network that has no inputs, just a clock. But for our combinational world, we have to have at least one input for it to make any sense. Okay, so in the combinational world, the outputs only depend on the current inputs, no historical information. But in the sequential design world, or the state machine world, we have some history of prior inputs, and we have some memory elements that hold that information from state to state, and we have some kind of feedback that actually allows us to have the memory. All right, and usually most digital devices in existence are sequential designs, they're state machines. Okay, key concepts to grasp. All right, so the way we do this design is we create this table of outputs that we want for all of our various possible inputs. And we call this a truth table. And we'll come back and talk about this more later in a couple of chapters down the road. But first, we're going to talk about number systems, bases, codes, and a bunch of other stuff. And then we'll come back to truth tables. Once we have truth tables, then we can implement the truth tables by using certain mechanisms. And one of the things we want to do is simplify our implementations to the simplest logic we can, because it directly translates into actual hardware, and we want the hardware as simple as we can get it. All right. So in our digital world, we're going to limit the number of states. We only allow devices to take 2 states, and they either are true or false, or 1 or 0. You can call it either way. There are some digital devices that have gone to tri and quad state now. Flash, the jump drives you have in your pocket or that you use are probably running on tri or quad state memory elements. But the rest of the logic and almost every other, all the rest of the digital world is a 2-state world. But some of our memory elements are now operating at 3 and 4 states. All of our design methods, all of our design tools are set up for a 2-state world. And this is part of the discipline to manage that we enforce to manage complexity. That's what the regularity principle. We keep everything set up so we only deal with 2 logic states. All right. There are a bunch of physical devices that we use to make our hardware. multiplexers, transistors, decoders, integrated circuits, diodes, all sorts of stuff. But within those devices, even though our voltages may vary over a range, we force our understanding of a given voltage level is forced to be either considered a 0 or a 1, a true or a false level. And because of this, it immediately suggests that binary numbers using the base of 2 might be a good thing to know about and to work with. We also have other tools to handle this complexity. And one of those tools is hardware description languages. There are two, Verilog and VHDL. There's also some things called System Verilog, System C that are coming along and starting to take over some of this. And these languages allow us to describe how we want hardware to be made using essentially English language statements. And then we have very, very powerful synthesizers that take our English language statements and can turn it into hardware, either by programming a big programmable hardware chip so that now it's doing what we want it to do, or by generating all the photomask and steps required in the foundry to manufacture an integrated circuit. Most of the integrated circuits made in the US are made with Verilog. Okay, so I wanted to talk a little bit about Moore's law. So Moore was he's one of the early principles in the world of transistors and integrated circuits, and he observed that in the early going, every 12 to 18 to 24 months, we were doubling the number of transistors per square millimeter on our integrated circuits. And it turns out for the last 50 years, every 1 to 2 years, we have in fact doubled the number of transistors. It is crazy. When I did my PhD, and I guess I finished it in 1981, I was using a microprocessor that had about 4,000 transistors. That's how many made up the microprocessor. I use a 6502. 6502 has about 4,000 transistors. The latest NVIDIA card there's one that's out. It's a dual core thing. Each core has 7,000. Each core has 7 point something billion transistors on it. So the total chip has about 14 billion transistors. 14 billion transistors compared to my 4,000 in the microprocessor I used. And you can see that that's about what we're doing. We are exponentially increasing it, but we're really up against a rock and a hard place now, because we're down to 10 nanometer features. We can't really go a whole lot smaller than that because we're up against two really hard limits. One limit is one nanometer spans about 3 silicon atoms in a matrix, in the crystal matrix. So our 10 nanometer feature cuts across about 30 atoms of silicon. So we're getting close to where we just have a handful of atoms in our feature. And obviously you've got to have several atoms in your feature anyway. So there's a limit to how much more we can go there. The other problem is we're using photolithography, and there aren't good replacement processes in place that don't use photolithography. And we just can't get smaller features really. It looks like we're up against a hard place on that. Obviously, there are some things that could happen that, we could get into, I don't know, organic materials. We could get into processing single atom at a time type technologies. There are some techniques for doing that, but we've got to, so I don't know if we're going to see this continue. We may see the dies getting bigger to make our chips more powerful. That's one thing that may happen. So we'll see. But in any event, whether Moore's law continues or not, who knows? It has been pronounced dead many times over the last 50 years, only to show that it continued to march forward. So it probably will continue somehow. When you think about this change, you realize what a dominant force the digital world has become. When you compare a digital device to an analog device, the digital device is tremendously more complex than the analog device. We looked at this temperature sensor here. If you compare that to the little analog column, glass column with alcohol filled up and a little reticle behind it so you can read the temperature, and then some attempt to slide it up and down to get it calibrated more or less. That's a pretty simple thing to manufacture compared to this. This thing has a lot of features to it that you don't think about. First of all, it has a temperature sensor down at the bottom. It has a display up here. It has a user interface button here. It has a built-in microprocessor and a battery. It has, besides the display, it also has somewhere a little piezoelectric buzzer to make the little beep when it's time to read your temperature. But beyond all that, then it also has a processor in here to take the sensor information that's a voltage change, to do the A to D conversion on that, to get it into a digital format, then to crunch the digital format to scale it and modify it so it's going to read in centigrade or Fahrenheit, so that it's going to read correctly, to round it to the nearest tenth of a degree, and then to format the display, because this can go up to, well, in centigrade it's just 3 digits, but it could go below 0, so it would have a negative. Well, maybe not this one, but some of them. And in Fahrenheit, it could certainly go to 4 digits, from 98.6 to 101. So, but when you display this, you want to blank the digit. If there's a leading 0, you want to blank it. So you don't want 037.0. That's not nice to look at. So we blank that 0. So you have to have enough smarts in your processor to take the actual data that's going to be displayed, and then do some really nice formatting on it. Blank leading zeros, put on minus signs if they're required, and convert it to Fahrenheit if necessary, all sorts of things. Also, you want it to be able to calculate the first derivative, and when the first derivative gets to 0 for a few seconds, then you can buzz the little buzzer and tell them you can stop. You can stop waiting on the temperature to stabilize. And then you probably have something that senses the battery voltage and signals when the battery is going bad, so you can replace the battery. It just goes on and on. There's a lot going on inside this little device, lots of parts to it. And yet, if you actually go back and compare the cost of this thing to the cost of an analog thermometer, you will find the analog thermometer is probably more expensive today. It's crazy. The analog thermometer probably costs more to manufacture than this thing does. And that just gives you another amazing sense. Despite all this complexity, this is still able to be made cheaper than, say, the analog equivalent.
Is there any specific reason why that is, or?
Yeah, so it's because we can make integrated circuits so inexpensively, because we can make hundreds of them. If they're small, we can make hundreds of them on the same silicon wafer, and we can produce that fairly inexpensively. And then we can cut them up. We can put on the bonding wires automatically. We can mount them on. We can make printed circuit boards and mount them on printed circuit boards using stencils and pick and place machines and reflow ovens and surface mount components. And we can do all this super efficiently, all automated and fairly inexpensively, despite the amazing level of complexity. Yeah, it's crazy. Just crazy. So in Micro 1, we every semester we make 100 boards. There's about 50 parts on this board. We put about 30 some odd parts on, 35 parts on or so, or maybe 37, I guess. And then we give it to the student, and the student solders on another 16 parts, and we have our Viva board. And we make 100 of these a semester. And we can do it in one evening because I have a pick and place machine, I have the stencil, I have a reflow oven, and we have all the parts on tape and reel. And boom, it's very easy to manufacture these things. Just amazing. So we have these great tools. And so everything is turned into digital because it's more powerful in terms of features, costs less noise, more flexible. You can change it easily, just change the firmware. You've got a completely new tool. It's much smaller in size, uses a lot less wattage from our batteries or from the wall. And there's just more and more reasons. This is just a good start of all the reasons why everything's going to digital. So there's just hardly anything in analog left. But you think, well, but the real world is analog. What about that? We live in an analog world, right? Almost all our sensors are analog. But of course, our MEMS technology is changing this because now we're making these micro machine devices also on silicon wafers and using the same foundry techniques that we do to make integrated circuits. And so our sensors are almost not even analog anymore. They're almost becoming digital. There are a few purely digital sensors that we have even now. And then even if the sensor is analog, we build a little A to D converter in it so that we digitize that signal before it even leaves the sensor and goes to the microprocessor. Or we may connect it to the microprocessor, and the microprocessor will convert the analog signal straight to a digital signal right off the bat with an A to D converter. But even if you think about this, there are actually a lot of features in the real world that are not analog actually. If you think about your brain and your muscles, most people don't know this, but I know it because I'm a doctor, took neural anatomy and physiology. And the truth is, every single muscle in your body is made up of, hundreds of thousands of fibers. And each one of those fibers is either fully contracted or fully relaxed at any given moment. So the way you can play a violin or have very fine control with your fingers is because you have a digital brain that sends out a very sophisticated digital signal to these hundreds of thousands of muscle fibers and only fires a few of them at any given time to just provide exactly the right pressure. And then not only does it do that, but it actually varies the ones that it's firing so they don't get totally fatigued. And it can change those. So you're firing different groups, but in such a way that you don't feel any change in pressure of the very delicate control you're exerting. And it does all this using the individual discrete nerves, which connect to individual discrete bundles of the muscle fibers, which basically turn them on or turn them off completely. And again, so the way that we get a range of contraction force is by changing the number of fibers we're firing, but not the degree that we're firing them to. So it's essentially a fiber is either contracted or it's not. It is purely a digital device. Unless, of course, it gets sick and has problems. And then if you think about matter, matter is made up of discrete particles, all of which obey very quantized quantum mechanic rules. Why do we call it quantum mechanics? We call it quantum mechanics because the equations that describe the behaviors of these particles and their interaction with each other only have solutions at discrete points. Most of the number space, they have no solution. They only have solutions. Usually it's usually got to do with some integer fraction times pi. And that in itself is kind of amazing and shocking. But quantum mechanics means that the whole physical world is quantized. Matter can only exist in certain discrete states, just like our digital signals. They're quantized. It's just like music. You know, you might think music is analog. Music is non-analog. If you've ever looked at a music score, you know that it only has, it has whole notes, half notes, quarter notes, eighth notes, sixteenths, 30 seconds. Maybe that's it. A really exotic thing might have 64ths, but that's it. There aren't any notes. I mean, I don't think anybody writes 128th notes. It's more of an ad lib thing at that point. So music is quantized. It is absolutely a digital medium. Just the notes themselves are quantized in digital. And then we don't want you playing out of tune. Out of tune means you're not on frequency. So the note you're playing is a specific frequency. And if you're off by one or two cycles, it may sound bad. So it's quantized. It's very digital. And then what's really interesting is now we're going back the other direction, because now our digital devices are behaving like analog things. AI and robots are, mimicking human behavior in such a way that you almost can't tell them apart. So it's a strange world we live in, but one thing's for sure, digital is here and it is getting more and more dominant every day. And you guys are going to be caught up in this. One last thought, I'm going to close with this. Serial and parallel algorithms. So even though your brain is an absolute digital device, it's set up as massively parallel. You have a massively parallel brain, but you think in serial thoughts. You think when you solve a problem, you solve it in a serial algorithm. You don't think it, your brain actually thinks in parallel, but you don't perceive it in parallel. You perceive it in serial. And up till now, we've programmed our computers with serial programs. But we're up against some hard limits now in terms of processing speeds until maybe we get to quantum computing, which is still in its infancy. And our serial algorithms are killing us because we can only execute steps one step at a time in order so fast. And we're really pretty much up against it because even our fastest logic gates still take a few nanoseconds to work. And so when you have a bunch of those lined up in series, you're just stuck with a certain amount of processing time. But if you can rewrite your algorithm so you can do all the steps simultaneously at once, instead of having to do step 1, step 2, step 3, step 4, that's a serial algorithm. If you can do step 1, 2, 3, 4, 5 through 522 at the same time, that's a parallel algorithm. And you can always speed up parallel algorithms. You just go buy another computer. And in this case, another computer is just another core, and another core can be fairly inexpensive. You can get pretty fancy cores for $1. You can be executing your 512 steps with 512 cores. And that's going to really speed it up so much faster than trying to get a single core that can be souped up and run 512 times as fast. That's hard to do. We've pretty much taken all the low-hanging fruit there already, and there's very little more gain to be had. We're pretty much stuck. We can only crunch things as fast as we can crunch them. And now, if we want to really see a big speed, we've got to go to parallel algorithms from serial, which means we have to think about things very differently than we do. Some things may not be able to be switched into a parallel algorithm, but to the degree we can, that's what we have to do. All right, I think is that it? Yeah, that's all I wanted to cover. Does anybody have any, let me kill this and give you a chance to ask questions.
I have a question.
Sure, go ahead.
So, you said that the PowerPoint presentations would be available on Blackboard, correct?
Yeah, I put that one on there. It's on there now.
Oh, okay. All right. Thank you.
And as I do them, I'll put them on there. These will all be brand new because this is the first semester to teach out of this book.
Okay. Oh, and also, I had some trouble with the Zoom link because I clicked on the one on Blackboard, but I think that was the one for your.
That's office hours.
Yeah, yeah.
Yeah, the one I sent out in the email is the correct link.
Okay. Yeah, just wanted to make sure.
Yeah, yeah. So, make sure you're getting the emails. I sent out two. I didn't send out one for this one. Actually, I planned on it, but didn't. But I'll probably send one out for Friday, just to remind everybody.
Yeah, Professor, I had a question concerning the textbook.
Okay.
So I went on the Blue Book and I tried to go purchasing the textbook that way.
Yeah,
And it says that it was out of stock. Now, it has this website that is offering the textbook.
yeah. If
But,
you look in the chat room, so let me. So I think let me see if I can pull this up.
Because I don't want to purchase something and then I
Yeah.
get gypped from my funds because it's like
Yeah, here I'll share my screen. So here's.
Yeah.
Yeah, so that's the website.
Okay. Okay.
Yeah, I think the bookstore only ordered a few of them. And they're probably out now.
It's actually cheaper through the publisher than it is on the bookstore. It said it's 102 on the bookstore.
Oh, really? So the
Yeah.
bookstore jumped its price up. Yeah, so it's probably usually the publisher is the cheaper source. Yeah,
Okay. So this is a publisher that you're using right here.
yeah, this is it.
I think
And
I
it's in
saw
the
it.
it's in the chat room or the chat.
Perfect. Let me see. I think I had it. I was in the final stages of purchasing it, and I just needed to make sure that I had the right thing because I wasn't too sure.
Yeah.
And once I purchase it, I will have to go to that site to be able to access it, or would it be available?
Yeah, there's you go on the Gray River Learning site and then you click UTSA and you click my book, and once you have once you bought it, then you should be able to see it. And it's good for the whole semester. I'm going to ask them to leave it up for like 6 months after the course, but then it will go away. If for some reason you drop the course and then you retake it later, you don't have to buy it again. You just have to let them know you bought it before, and they'll check that out, and you'll be set to go for round 2.
Okay, one more question before you go.
Sure.
In terms of the textbook, I forgot it. Once you purchase it or whatnot, and I forgot what I was going to ask you. Anyway, I'll just figure it out. Thank you though.
Sure, no problem.
Let's see, is that this one? Oh yeah, all right, I found it now.
Go.
Professor.
Yeah, go ahead, Kyle.
Sorry. I just had a question on the syllabus. On the first things to do is the syllabus quiz.
I actually haven't written that yet, so don't worry about that till I'll tell you when I get it, when I put it up on the website, and then you can do it.
Okay.
It's kind of a recommendation, so I went ahead and put it in the syllabus, but I actually haven't generated it.
And as far as, I'm sorry.
No, go ahead.
As far as the homework goes, is that also going to be just within the textbook?
Yeah.
Like at the end of the chapters?
Yeah, that's what I'm planning, with maybe 1 or 2 added assignments just for grins. But yes, that's what I'm planning.
When we do the end of chapter quizzes in the textbook, does it like, I don't think it links to the class or anything, does it?
What it will do, it generates it automatically grades it. And then what I'll do is I'll download it into a spreadsheet, and I'll probably upload it to Blackboard just on my own eventually. But when I do the grades, I'll have that as one of the columns for homework. It'll come off of the book site.
Okay.
Yeah. So in theory, it probably eventually will get automatically populated into Blackboard. It just takes it just takes Blackboard a while and Great River Learning to get that hooked together. They're working on it. But it, you know, there are a number of institutions with Blackboard and Great River Learning books where that happens automatically, but no, it had never been done at UTSA yet. So, so they're plowing new ground, and they're, you know, eventually they'll get that working. But I told them not to worry about it because for my purposes, I always do the final grades on Excel in a spreadsheet anyway. And I use Blackboard, but the first thing I do is I download the data off Blackboard into my spreadsheet. It's just as easy to take a column from another spreadsheet and add it in as it is to, you know, to do the, well, they're working on getting it automatically populated, but I just, you know, I didn't want to spend time on that because it's very frustrating, but eventually they should make it work. There are mechanisms for that.
Okay, I just wanted to make sure that there will be a way to like
Yeah,
turn it in and all that.
yeah,
Okay.
it just automatically turns in when you do it in the book.
Okay, cool. Thank you.
And it's automatically graded. You should know. And I think just for grins, I let folks have a couple of shots at it. Because again, the whole purpose of, I mean, I know, and you know, that as soon as something's out, within a few months, all the information, all the right answers will be unchecked, right? I mean, everybody knows this. So the idea that there's some kind of game evaluating you, whether you get the right answer or not, that's not the point of the homework. The point of the homework is for you to think through and work through these problems. The first few chapters are more questions, not too much problem, but then, well, there are problems in some of them, but then later on, it's going to be all kind of problems. And what I want you to do is work through it and you know, work to try and figure it out and get the right answer. And then even if you do or don't get the right answer, that's not my primary concern. My primary concern is that you went through the effort of you know, pushing through it. And then if you didn't get the right answer, I want you to understand what you did wrong and get it right, as opposed to, you know, using that to decide who's smart and who's stupid. That's not really the point. So
I think that's a good approach.
yes, sometimes stupid is a good approach. Although it's usually better to be smart. But sometimes you can be too smart. So what I want is good level-headed learning. So, because these are building blocks you're going to use for the rest of your career. All right, any other questions?
Okay, so I just purchased the book and I'm on the website right now. Where do I go? I already logged in. Where do I go to get the?
So there should be a thing where it says put in your institution. Here, let me, you can share your screen. We'll see what you got. Let me unshare mine. Oh, I guess I'm unshared. So let me change it so you can share. Hang on one second. Advanced sharing options. Okay, go ahead. Now you can share your screen. Let's see what you're seeing.
Okay, so I just purchased it right now.
Yeah.
This is the screen that I have here.
Okay. So, so
The student, I click here and it says frequently asked questions.
yeah, let's see. So click on
Home, maybe?
yeah, click on home. And okay. Maybe click on click on the Great River. Well, I don't know. See, oh, my orders. Click on my, see the line, the red line at the top where it says my account, my orders. Now click on my orders. And did you click on it?
Yeah, my orders.
Oh, it says you haven't placed any orders yet.
I just got the confirmation that I purchased it already. So
Okay, so maybe I don't know, maybe you have to log out and log back in. I don't know.
If you
Not
got information, at least that means that you should be able to get it, and like you could like.
that's why
Yeah, I'm sure it's workable. Click, why don't you log out and log back in, see what happens.
I'm back in my orders. Haven't placed any orders. Da, da, da.
So in your email, maybe there's a thing where you have to click on that.
Yeah, I didn't get any email about it. Let me see something.
Yeah, I'm curious because I haven't actually gone through this process, obviously.
You successfully created an account designed. Da, da, da. Is it really, Adjustment heading.
Okay, yeah, so the one you have to do, go to, Shane, go to, look in the chat. Somebody just posted the website you have to go to. It's www.grlcontent.com. Yeah, so the one you're on is just to purchase the book. Yeah, go
Chat,
to,
you said
yeah, you see the one in the chat?
this one?
Yeah, I think so. Is it www? Yeah, that's it. You're on.
Oh, okay. All right, and blah blah blah.
So that's the welcome screen. And then see where it down it says chapters. Click on chapters. And then you can click on chapter 1. That's it. And you can read that. It's the first chapter is pretty short.
So how come so because I purchased it, they're giving me this access? I don't know how they know that
Yeah, right.
that's
I don't know
weird.
either.
That is weird. I'm not even logged. They didn't even allow me to log in or anything. So what if I was trying to log in from a different computer now?
I don't know. I guess if you have issues, let me know, and then I'll contact the Great River Learning folks and find out. They also have, I think you can send them, if you're having problems, you can send them a thing.
All right, well, I just purchased it. I don't want to lose access, and
It should
and then I
be
have to pay
fine.
for it again.
Yeah, no, they won't make you do that.
All right, okay.
Sounds good.
Thank you.
All right.
Yeah, I've been trying to do this for like since day one. It's just like
Oh, good. And you
yeah,
just
all right.
and you just sent $8 to the Paul and Phyllis Morton Scholarship, Computer Engineering Scholarship Fund.
Lovely, lovely.
So maybe
I
you can
thank you.
qualify in a year or so.
I hope so.
Yeah, you never
Because
know.
that's my major.
Well, that's good. All right.
All right.
Okay,
Thank you.
we'll see y'all later.
All right. Bye. Are we gonna have that resuscitation or whatever later or no?
So the TA, not this week, the TA is going to send out an email and tell you when it's going to be for next week. He's going to do it online for the next 2 weeks, and then hopefully he'll be face to face. Or if you guys want to continue to do it online, I don't care. You can do that too. Just tell the TA what you think you'd rather do.
Okay.
But he's supposed to send out an email. If you don't get one by Friday, let me know.
Will do. All right. Thank you, Professor. Once again, I appreciate it.
No problem. All right, we'll talk to you later.